A hot claim online. Two cars colliding head-on at 60 kilometers per hour equals one car hitting a wall at 120 kilometers per hour. Is this claim true or false? In this episode of Experiment and Truth, we use kart experiments to break down the two core physics behind collisions: momentum and kinetic energy. Our subject: this car on the track, a miniature real car. First, momentum. P equals mv. It measures the quantity of motion. Heavier or faster objects have greater momentum. How does momentum change? Through impulse force accumulated over time, with the formula I equals F times delta T. The impulse momentum theorem, F delta T equals delta P. Longer force duration gives greater momentum change. Application: collisions and impacts, where force acts over a very short time. Experiment: cart hits a spring bumper. Longer collision time, smaller force. Hit the clay bumper, extremely short time, very large force. But the impulse area under FT curve is identical, same momentum change. Core law: with zero net external force, total momentum is conserved in both elastic and inelastic collisions. Now kinetic energy, F times S equals 1/2 m times delta T squared. It describes the energy of motion, the ability to do work. How does kinetic energy change? Through work force accumulated over space. W equals F delta X. The work energy theorem, W equals delta K. Longer displacement gives greater kinetic energy change. Application: processes with force over displacement and energy conversion, braking, acceleration. Core law: with only conservative forces, gravity, elasticity doing work, mechanical energy is conserved. Now we grasp their essential difference. Momentum relates to time, how long the force acts. Kinetic energy relates to space, over what distance the force acts. One is force over time, the other is force over space. This difference gives them entirely different applications. In collision problems, we focus on time, use momentum conservation. In motion processes, we focus on displacement and energy conversion, use the work energy theorem. A quick rule: momentum for collisions, kinetic energy for processes. Now let's explain the opening question with these concepts. Momentum analysis: equal mass, equal speed, opposite directions. Total momentum is always zero. After collision, still zero momentum conserved. Kinetic energy analysis: each car has 1/2 mv squared. Total is mv squared. After collision, both stop. All kinetic energy is absorbed by both crumple zones together. To see the essential difference, we analyze from two dimensions. Path 1. Impulse momentum. In a head-on crash, each car goes from 60 kilometers per hour to zero. Momentum change equals mv. In a 120 kilometers per hour wall hit, the car goes from 120 kilometers per hour to zero. Momentum change equals 2 mv, twice that of the head-on crash. Greater momentum change gives greater impulse needed. With similar crash time, impact force is also greater. Path 2. Work energy. In a head-on crash, both crumple zones together absorb mv squared. In a 120 kilometers per hour wall hit, a single crumple zone must absorb to 1/2 mv squared alone, twice the energy. Both paths lead to the same conclusion. A 60 kilometers per hour head-on crash is far more gentle than a 120 kilometers per hour wall hit. For a 120 kilometers per hour wall hit, a single car's kinetic energy equals 1/2 meter to v squared equals 2 meters v squared. The total kinetic energy absorbed in a 60 kilometers per hour head-on crash mv squared is only half of that in a 120 kilometers per hour wall hit 2 mv squared. So not equivalent. The key is kinetic energy differs by a factor of 2, so destructive power differs. This misunderstanding is a classic case of confusing momentum and kinetic energy. With momentum and kinetic energy understood, we can answer: should a car be hard or soft? The answer: hard where it should be, soft where it should be. The soft front and rear are carefully designed crumple zones. They fold like an accordion during a crash, extending collision time. from F delta T equals delta P. Longer time means much smaller impact force F on occupants. The hard passenger cabin, A pillars, B pillars is a sturdy life fortress. Their job, keep the survival space intact. German and Japanese automakers converge on the same principle. Soft front, hard rear, combining rigidity with flexibility. If the whole car were hard, crash energy would transfer directly to the body. Internal injuries. If the whole car were soft, the cabin would be crushed, life-threatening. The crumple zone sacrifices itself to protect the cabin. Same design philosophy as our different bumpers. Let's summarize this episode of Experiment and Truth. First, momentum is the quantity of motion, changed by force over time, conserved in all collisions. Second, kinetic energy is the energy of motion, changed by force over space, conserved only in elastic collisions. Third, a 60 km/h head-on crash is more gentle than a 120 km/h wall hit from both paths. Total kinetic energy is only half. Fourth, the soft parts protect you from impact. The hard parts protect you from being crushed. That's the essence of safety. From the lab cart to real cars, the laws of physics hold. We hope this episode helps you truly distinguish these two most important physics concepts. Like, follow, and explore the truth with us through experiments. See you next time.